Example, test the series. The sum from n equals 1 to infinity, 1 over n squared plus 1 for convergence or divergence. So again, the questions now are not going to say anything about finding the sum, because in general you can't do that unless we have a geometric or telescoping, which this one is not, either one of those. And so I said at the beginning of the class, we're building up to a bunch of techniques, and it's kind of like when you were integrating things, you have to decide which technique to use when. So I think I mentioned when I told you the divergence test last time that I like to start with that one always. If I have no idea, I don't recognize it as like a geometric or a telescoping, I'm just going to start with the divergence test. So the divergence test, we take the limit of our terms, 1 over n squared plus 1. And what's that limit going to be? 0. The divergence test says if I get anything other than 0, the series diverge. But I got 0. So here, the divergence test is inconclusive. It doesn't tell me that my series diverges, so I've got to try something else. Really, we don't have a lot of techniques now. So the thing I'm going to go to after trying the divergence test is going to be the integral test, because those are the only two methods right now I have. So I convert this into a function. Is this function going to be continuous? I'm dividing. What's the only number we can't divide by? 0. Is the denominator ever 0? No, it's always at least 1, right? So this function, it's continuous, and the denominator is also positive as well, and the numerator is positive, so it's going to be positive on my interval 1 to infinity. So the next thing, I need to double check the other condition in the integral test was that it needed to be a decreasing function. The way to show a function's decreasing is to take its derivative and show it's negative. Okay? So I want to take the derivative of this. It might help you if you rewrite this as x squared plus 1 to the negative first. And now what's the derivative of this function? Negative 2x, over x squared plus 1 squared, right? Because it'll be to the negative second power. And I move it to the denominator. The denominator is a square, so that's guaranteed to be positive. The numerator, well, I'm only interested in the interval from 1 to infinity for x. So the numerator is going to be negative, right? So this is going to be less than 0 on this interval 1 to infinity, i.e. it's decreasing. If the derivative is less than 0, your function is decreasing. Okay? So now that I've checked all the conditions of the integral test, continuous, positive, decreasing, I can now use it. So let's integrate from 1 to infinity. And our function was 1 over x squared plus 1. Again, we have an improper integral. Every time you have an improper integral, you have to put in a limit. What's the integral of 1 over x squared plus 1? Okay, remember? Arctangent. Okay. So this is going to be arctangent of x. So what we're going to do now is we're going to plug in our bounds. The limit as t goes to infinity, arctangent of t minus arctangent of 1. Oh, let me scoot that over for you. Okay. What's arctangent of 1? What angle gives me tangent is equal to 1? That's the value of sine and cosine. What's my angle? Pi over 4. So I'm getting arctangent of t minus pi over 4. And do you remember what the limit of arctangent is as t goes to infinity? It's pi over 2. So it's left with a pi over 4. So my improper integral converges. What does that mean for my series? Does it converge or diverge? Converges. Okay, whatever happens to your integral, improper integral, the same thing applies to your series. So now we can say our series, which was n equals 1 to infinity, 1 over n squared plus 1, converges by the integral test. Okay. And again, you should get in the habit of writing what test you're using when you say converges or diverges. Okay.